lecture number 7, AP Chemistry, and we are discussing structured questions related to elements and mixtures. So first of all, in question number 1, a student is given a solid sample consisting of two elements X and Y. The sample is analyzed in a lab and the data is recorded. The total mass of the sample is 1.5 and the mass of X in the sample is 0.90 and the mass of Y is 0.60. Identify one physical property that can be used to determine whether the sample is pure element or mixture. So first of all, the property that is going to be used to determine whether it is a pure element or whether it is a mixture, that is by measuring their melting point or boiling point because what happens that if it is a mixture then what happens, the boiling point will be increased, and if it is a mixture then melting point will decrease. So calculate the mass percentage of element X in the sample. How can we do that? So the total mass of X is 0.90. The total mass is going to be 1.50 and times it with 100. And the answer comes out to be 60%. Then they are saying they have given us the atomic masses and we have to determine the simplest whole number ratio. That means we need to determine the basically empirical formula, because empirical formula tells us the simplest whole number ratio. So we are given with the mass. This is X and this is Y. Mass of X is 0.90 and mass of Y is 0.60. So first step is dividing mass with their molar mass. X is 24.3 and that of Y is 32.1. So in order to determine it, we need to divide it. So the answer comes out to be 0.0370 for X, and the moles of Y is going to be 0.0187. So dividing with the smallest amount is 0.0187 and here also 0.0187. So it comes out to be 2:1 and this is so this is the ratio between X and Y, which is 2:1. So in this question, a student analyzes a sample of an unknown metal oxide which is composed of metal X, which is calcium. It's not given in the question, but it is calcium. So the student conducts an experiment to determine the molecular formula of the compound. There is an empty crucible. You can see this is an empty crucible. And the crucible plus metal X before heating. There is metal X present here. Metal X is calcium. And we know when calcium is heated with the help of the burner, then it reacts with oxygen and is going to form metal oxide. Okay. Now, what happens here that we need to find like they are saying crucible plus metal X before heating, it was having the mass of 24.67. So in order to find the metal X, the mass of metal X, what we need to do, we are just going to subtract 24.67 minus the empty crucible, that is 22.15. So mass of metal comes out to be how much? That is 2.52. And then what happens? Crucible plus metal oxide after heating. So when it becomes metal oxide, then we need to find like what is going to be the mass of oxygen that has been added into it. So for that purpose, what we are going to do, we are just going to subtract the both of them. 25.35 minus 24.67, that tells us about the added oxygen. 25.35 minus 24.67, that is mass of oxygen, and that comes out to be 0.68 grams. Now we need to find the empirical formula, and how we are going to do that. This is metal, that is 2.52 grams, and then we have oxygen, that is 0.68. So I'm dividing metal with the molar mass of metal, which is calcium, so it's 40.1, with oxygen, that is 16, and the answer that comes out to be, the answer that is here will be 0.0629, and then we have 0.0425. So now the next process is dividing with the smallest amount, and that is going to be 0.0425. So 0.0629 divided by, we have 0.0425 ratio, 0.0425 divided by 0.0425, and the answer comes out to be 1.5 ratio 1. But still it is not in whole number, so making it into whole number we have to multiply it with 2, and the answer comes out to be 3 ratio 2. So it is going to become X3O2, X3O2. Now we are given with and the molecular mass of the compound, that is 305.2, and then we are also given with the empirical formula, that is X3O2, and we know the formula, N is equal to molecular formula mass divided by empirical formula mass. Molecular formula mass here is going to be 305.2, and empirical formula mass is going to be calcium 40.1 times it with 3, because there are 3 atoms, plus 16 times 2, and the answer comes out to be 305.2 divided by 152.3, and that comes out to be 2. Now applying the next formula, which is going to be N is equal to molecular formula divided by empirical formula, and N here is going to be 2. Molecular formula we need to find out, empirical formula is X3O2, and molecular formula here becomes 2 times X3O2, and that would become X6O4. So in this question, a student analyzed sample Z, which may be pure copper and zinc and is a mixture of both metals, and their melting range is 890 to 950. That means it is not fixed, because we know that if it is going to be a pure substance, then definitely it is going to have fixed, it is going to have fixed melting point and boiling point, but here it is not fixed, so it is definitely a mixture, because mixture has range of melting point or boiling point. Why zinc reacts with HCl but copper does not? The reason is that you can see this is the reactivity series I have written on the right hand side. The elements above than hydrogen, they can only react with acid. Okay, so copper doesn't react because we can say that copper is copper is less reactive than copper is less reactive than zinc. The reason is that copper is, like you can say, copper is less reactive than zinc. Reactive than zinc. Right, electronic configuration of copper atom. So for that purpose we need to find its atomic number. So let's see the atomic number of copper. So the atomic number of copper is 29. So let's write the electronic configuration. 1s2, 2s2, 2p6, 3s2, then we have 3p6. Then we know the 4s. First we are going to write 4s1 because we always write it first, and then we are going to write 3d10, because what happens in copper, the electron from 4s would transfer to 3d. It happens in copper as well as in chromium. Identify the type of alloy of copper and zinc. So copper and zinc both have the same size, almost have the same size. So the alloys which are going to have same size, that kind of alloy are called as substitutional alloys. So the alloys which have same size, they have same size. So the alloys which have same size are called as substitutional alloys. This question, a chemist analyzes a mixture of two metals, iron and copper, in which the iron to copper mass ratio is 3:2. The metals are reacted with excess nitric acid to form soluble nitrates, iron nitrate and copper nitrate. The chemist then evaporates the solution, leaving behind the dry metal nitrates. So this is the mass of evaporating dish. This is evaporating dish, and he has basically put the metal inside it. In this one, there are the metals, iron and copper. They are in the ratio 3:2. So if we want to find out the when the original metal contain a mixture of metals, so the mass of the metal here is, so in the first question they are asking us that we have to determine, suggest an experimental method to confirm whether the original sample contained a mixture of metals. So it's very simple. We have discussed in the previous question as well that we are going to measure the melting point of sample, melting point or boiling point of sample, or boiling point of sample, because we know that a pure metal is going to have the sharp melting point and boiling point. But if it is a mixture, then what happens, I have told you that melting point will decrease and boiling point will increase. So this is what happens when you are trying to measure the melting point of the mixture. Determine the total mass of the metals in the sample. So if we want to find the total mass, so this is the evaporating dish which contains the metal. So if we want to find its mass, how can we do that? 57.89 minus 50.25, and the answer comes out to be 7.64 grams. Then he's saying explain why this mass remains unchanged before and after the sample. So what happens there? There is no loss of metal during the process. That is why the mass of the metal they remains conserved. We can write here that there is no loss of metal atoms during the process. As the metal is only changing from metal to metal nitrate and there is no loss of metal during the process. So using the iron to copper ratio, they are saying calculate the mass of iron in the sample. So we know the total mass of is 7.64 and iron to copper ratio they have given 3:2. So if we want to find out the mass of only iron from the total mass, uh, like you can say the ratio is 3 of iron and the total is going to be 5 because 3 plus 2 is 5. It's 3 plus 2 is the total, which is 5 here, and 3 is for iron, and 3 by 5 times it with 7.64, and your answer comes out to be 4.58 grams. Calculate the percent by mass of iron in the original sample. So if we want to find out the percentage of iron, the mass of iron is 4.58 and the total mass is 7.64, times it with 100 and the answer comes out to be 59.9%. So in this question, a student analyzed a 1 gram sample of compound X, which is known to contain only carbon and hydrogen. Tests are performed to determine the mass of each element in the sample. And the students find that the sample contains 0.857 gram of carbon and 0.143 gram of hydrogen. Calculate the number of moles. So if we want to calculate the number of moles, first moles of carbon and moles of carbon are mass 0.857 divided by its molar mass, which is 12.01, and the answer comes out to be 0.0714 mole, and the mole of hydrogen will be how much? Mass divided by molar mass 0.143 divided by molar mass, which is 1.008, and that comes out to be 0.1419 moles. Determine the molecular formula of the compound X. So we have to determine the molecular formula of compound X, and for that purpose what we need to do, first we need to find the empirical formula. There is carbon, there is hydrogen. Carbon moles are 0.0714 and hydrogen is 0.1419. So I'm going to divide it with the least number of moles, that is 0.0714, and this is also 0.0714, and that comes out to be 1:2. That means empirical formula is CH2. So we know the formula, that is going to be N is equal to molecular formula mass divided by empirical formula mass, and that comes out to be it's 56.1, which is given. And if we want to calculate the empirical formula mass of CH2, then it comes out to be this is 12.1 and this is 1.008 for hydrogen, but there are two hydrogens, so that comes out to be 14.0 026, and that is equal to 4. So n comes out to be 4. Next formula is molecular formula divided by empirical formula. So if this is 4 and molecular formula, we need to find out empirical formula is going to be CH2 there. So molecular formula comes out to be C4H8 when 4 is multiplied with the number of atoms. Then they have given us like this is the molecular formula. Then they are saying calculate the number of carbon atoms in the original 1.20 gram of sample of compound X. This is compound X. So first we need to find its number of moles, and moles are here mass. What is the mass? 1.20 divided by molar mass of C4H8, and that would comes out to be 56.1 because it is already given to us, 56.1, and it comes out to be 0.0214 moles. So we need to find the number of carbon atoms. Number of carbon atoms is, how we can do that? Mole times Avogadro's constant. But here, how many carbon atoms are there in it? 4 carbon atoms. So I'm multiplying 4 with the mole, that is 0.0214, times it with Avogadro's number. So it comes out to be how much? That comes out to be 5.15 times 10 raised to power 22 carbon atoms. So the next question says that use the balanced chemical equation for the complete combustion of 1 mole of compound X to calculate the CO2 molecules produced during the combustion of this. So first let's write the combustion of C4H8 equation. During combustion, what happens? Oxygen reacts with it, and when oxygen reacts with it, it is going to form carbon dioxide and water. So first balance it. Okay, so there are 4 carbon atoms on the left hand side, so we have to balance it with 4, and there are 8 hydrogen on the left hand side, so we have to balance it with 4 here as well. First carbon needs to be balanced, then hydrogen, then it comes towards oxygen. So there are 8 oxygens and 4 oxygen, so 12 oxygen, so I have to multiply it with 6. Now if you can see here, then you are going to see that there are 4 carbon atoms on the left hand side, like 4 carbon atoms, and they are producing how much? 4 molecules of CO2. In the previous question, how many atoms of carbon are there? There were 5.15 times 10 raised to power 22 carbon atoms. You can see there is 1:1, like 4 carbon atoms are producing 4 molecules. So if there will be 5.15 times 10 raised to power 22 carbon atoms, then they are also going to produce 5.15 times 10 raised to power 22 molecule of CO2. Okay, because there is 1:1 there. In the next question, they are saying another student proposes that the molecular formula of compound X is C2H4. Explain why this formula is inconsistent with the data in the equation. We are given with the molar mass of X, which is 56.1, but now they are saying its molecular formula is C2H4. If we calculate its molar mass, then it comes out to be like 12.01 times 2 plus 4 times 1.008. So it comes out to be 28.052. And you can say that the molar mass given is 56.1, But for this molecular formula, it comes out to be 28.052. Okay, so that is why it is inconsistent with the data in the equation. State the molecular formula of a compound with the same empirical formula as compound X, but a molar mass of 70.1. And he wants us to find out that what is going to be the molecular formula of a compound now. So N is equal to, empirical formula was uh, like we have calculated CH2. This is the empirical formula. So it was CH2. So first we are going to use the formula molecular formula mass divided by empirical formula mass. Molecular formula mass, now they have given us 70.1, and empirical formula mass of CH2 was 14.026 is equal to 5. And now if we want to calculate it, then formula we are going to use N is equal to molecular formula divided by empirical formula, and it is 5 is equal to molecular formula divided by empirical formula is going to be CH2, and molecular formula comes out to be C5H10. In the next question, they say explain one limitation of using only elemental mass data when analyzing compound that may contains oxygen. So we can say that it only gives us the information about the elements present, but it doesn't give us the data about like how atoms are bonded, whether whether I mean like whether they it has OH, whether it has carbon double bond oxygen, whether it's just oxygen. So it does not help us to distinguish between the functional group, does not help us to distinguish between functional group. In the next question, they are saying a student analyzes a 1.68 grams sample of metal oxide containing only an unknown metal and oxygen. The oxide is reduced by heating in a stream of hydrogen gas, which removes the oxygen as water vapor. After complete reduction, 0.89 gram of pure metal remains. So these are the moles that are given to us, and they want us to find the empirical formula. So first we have metal ion, then we have oxygen ion. Metal ion is 0.0100, and then we have oxide ion, which is 0.0150. So we have to divide with the smallest value, that comes out to be 0.0100 and 0.0100. It comes out to be 1 ratio 1.5. We have to convert it into whole number by multiplying it with 2. So it comes out to be 2 ratio 3. In the next question, they say, would the empirical formula change if the student use a large or small sample size? So they are basically checking your understanding of law of definite proportion, which says that the ratio of masses between the elements, the ratio of masses between elements in a compound remains same. So this was basically explained by law of definite proportion. So here we are going to say that it remains Same, because the ratio of atom in a compound is constant. Because the ratio of atom in a compound is constant. Calculate the percentage by mass of oxygen in a compound. So we have to calculate the percentage of oxygen in a compound. So how can we do that? This was the total mass, and when it is reduced, then what happens? Oxygen would remove from it. Okay, like for example, this was metal oxide, and when it is reacted with hydrogen, then what happens? Only the metal remains and the water becomes. So we have to calculate that what is the percentage by mass of oxygen. So total mass was 1.68, and when it reduced, it becomes how much? 0.89. So if we can subtract them, then we would come to know about the mass of oxygen. So we can do it by 1.68 minus 0.89 divided by total value, which is 1.68, times it with 100, and it comes out to be 47.0%. So in B part, this is basically the percentage mass of oxygen. This is percentage of oxygen. But what is the percentage of metal? That definitely we can just subtract it from 100 minus 47, and that comes out to be 53%. So next question says that we have to determine the molar mass of metal and suggest its identity. So first of all, we know M2O3 is the you can say formula. Now, if we keep the molar mass of M to be X, let's keep it X, then it would become 2X plus 16 times 3. So it is 2X plus 48, which is the total molar mass. Okay, total molar mass. And the mass of molar mass of metal is going to be 2x. So 2x is the mass of metal. Now we know the percentage of the metal is going to be 53%. So I am going to use a formula: mass of metal divided by molar mass of compound and times it with 100, and it comes out to be how much? It comes out to be 53. So mass of metal is going to be 2x there. Molar mass of compound is 2x plus 48, times it with 100, it comes out to be 53. Then by solving the equation, the value of x that comes out to be is going to be 27.06, and that is for aluminium. Okay, explain why identifying the metal based on its molar mass provides evidence that the sample is pure. So the molar mass provides evidence that sample is pure because if we are identifying the atomic mass of metal, okay, which matches the expected molar mass, this suggests that the compound only contain one metal. So if the atomic mass of metal matches the expected molar mass, that what we have expected, molar mass, then the compound, that compound contains only that metal. The student repeats the experiment and recovers only 0.83 gram of metal from 1.76 gram sample of the oxide. Explain what this result suggests about the purity of the sample. Justify your answer. So before it was 0.89, but now it is 0.83. And if you can see that before the percentage was how much, that was 53%, but now if you see the percentage, it has dropped to 47.2% of metal. So it suggests that the sample is not pure, why? Because it contains 47.2% of metal, and it is less than 53%. Okay, and how we have calculated this 47.2%? We know 0.83 divided by the total is 1.76, times it with 100, so it comes out to be 47.2%. In G part, they are saying explain how a particle level model of the metal oxide differs from that of a mixture. It is definitely a particle level. Why? Because the metal oxide contains only one type of particle. This metal oxide contain only one type of particle, but in mixture, it varies. So it contains only one type of particles in which atoms are bonded together, in which atoms are bonded together in fixed ratio, are bonded together in fixed ratio, which is how much? In M2O3 in 2 ratio 3.